Hold on a second. Let me go back. Let's see, what is today's date? The 18th.
The 18th.
So we'd be looking for something on the 11th. Is this it?
4.1. Yes, that looks right.
That's 4.1. Are we still on 4.1 or have we gone to 4.2?
She broke 4.1 into 3 sections. So this time we'll be talking about the second 2 sections she broke it into, which is on this worksheet 35 to 56.
All right.
Oh, sorry, 35 to 59.
Okay, starting with that 35 right there.
Yes.
Okay.
Find the index. I need to set my notebook. Oh, there it is.
So how do we do this one?
E5 cosine x plus 4 sine x. The integral of cosine and sine. So we'd have to know the trig derivatives to do this, wouldn't we?
Yes. And these are definitely 2 that you want to memorize. If you memorize any 2, these are the 2 you want to know. What's the derivative of sine and what's the derivative of cosine?
Yeah. So since the derivative of sine is cosine, the derivative of cosine is negative sine, the opposite would be for these. So we would have 5 sine x plus I want to say cosine x, but since the derivative is negative sine, we would get negative 4 cosine x.
Yeah. In other words, you're just reversing everything. And this is a 5, not an integral sign, and plus c. So if I want to remove these parentheses, I remove the plus sign, and
minus 4 cosine.
There's my answer. And of course, always the way to check these is to take the derivative of this, and we better get back to the same thing.
Which it looks like you would.
Yes. Okay. Odd ones only, or every one from 35?
Everyone this time.
Okay.
She decided that since there was less questions, to do them all.
Uh-huh. Now these look relatively straightforward also.
Yeah. So we have t squared cosine t dt. So we would start with the t squared and make that into a t to the third over 3 minus so that would be negative sine t.
Just sine t. In other words, first of all, let's go back a step. One thing that's very important to realize here is that whenever we have the addition or subtraction I can break it up into two integrals.
Yeah.
Now let's do each one separately. This becomes t cubed over 3 minus, what's the antiderivative of that?
Sine t. Plus.
So there's your answer plus a c.
Mm-hmm.
Okay, looks like these are a lot of trig. Nice of them to use so many t's.
Okay.
Combined with a 1. Surprised they didn't put some l's in there. All right.
So the 1 just turns into a 1t, or just a t, right?
Uh-huh.
And then the cosecant cotangent. That's cosecant t. So minus cosecant t ut.
It's actually the negative of that. In terms of memorizing your trig functions, let me help you. Notice that the derivative of sine is cosine. The derivative of cosine is minus sine. The derivative of tangent is secant squared. The derivative of cotangent is minus cosecant squared. See the pattern here. The cofunction, the derivative of each cofunction is negative. And if I continue it into the two that are the hardest to remember, we have the derivative of the secant is secant tangent, which makes the derivative of the cosecant has to be negative cosecant cotangent. So notice that each cofunction, the derivative is negative.
Mm-hmm.
So when we're going back the other way, we started with cosecant cotangent, so that must be in other words, if I were to take the derivative of that, I would get that. See that?
Yeah.
Okay.
Isn't it? Yeah.
So the way to really verify that you have the plus or minus sign correct is to always take the derivative of what you get. And for a while, since you are just getting into integration, I would make that standard practice. Just, you won't make any mistakes that way. Obviously, if I take the derivative of this, I get 1. And then if I'm going to take the derivative of that, I'm going to get minus cosecant cotangent. And that'll go to 0, so that'll be my answer. That is what I started with. Everything's correct. But this little thing here for the 6 functions, it's very useful. Not only that, but notice the other patterns here. In other words, the cotangent is the cofunction of tangent, and the cosecant is the cofunction of secant. So there's a pattern between those two. Same thing here. The derivative of secant is secant tangent. The derivative of cosecant is the cosecant, cofunction of that. Cotangent, the cofunction of that. So the derivatives of all your cofunctions, and when I say cofunction, you know what I mean, right? In other words, sine, cofunction is cosine. Secant, cofunction is cosecant. Okay? So it's useful to be able to relate them as cofunctions of one another. They also have some other interesting properties, but this is actually makes it fairly simple to remember the derivatives. Particularly the derivatives, the signs of the derivatives. About 38.
38 is theta squared plus secant squared theta. So again, we would just, for the theta squared, make it a theta cubed over 3. And then for secant squared, we would make that a tangent square, or just a tangent,
Just
theta.
Just a tangent. Yeah, the fact that they use theta instead of a variable doesn't matter. As long as that's the same as that, then it's just like x or y or t.
Just so then we get the tangent theta again, and for sine we get, so that's plus cosine theta, right?
Exactly.
The sine, okay. I think I get the sine now. I was having issues understanding the way the sine is.
The way to really, I mean, it's almost you could guess. You put plus or minus there, and then take the derivative of this to see if you get this, and if you don't, change that sign. Is one way to do it. You know what I mean?
Yeah.
Okay.
I was just at first having issues I don't know why, just the way the signs flipped when you switched them on the cofunctions caused me issues.
Finally, a little difficult one.
So to solve this, would we just multiply the inside of the parentheses by the secant, so we'd have secant tangent minus secant squared. And then when we did the integral of that, we would be getting secant minus tangent.
Good. I don't know why I keep getting these DLL files that are trying to install on my computer, but all right. 35 through what?
Let me go look. She did 35 through 59, but since looking at this section here, it looks like 35 through 44 about the same, so we could probably move on to 45 here.
Hold on a moment. Let me look at 41. They're not quite the same. I think it's worth doing 41.
41.
Yeah, that's the next one in line. In other words, we just did 40.
Yeah. I see. 41. That's interesting. Tangent squared. What gets you tangent squared?
Think of your trig Pythagorean identities.
Trig Pythagorean identities.
There's 3 of them. Sine squared plus cosine squared equals 1. Tan squared plus 1 equals secant squared. And cotangent squared plus 1 equals cosecant squared. So which one is... So what can I substitute for tan squared plus 1?
Secant squared minus 1?
No. In other words, there's the identity.
Well...
Tan squared plus 1 is equal to secant squared.
Oh, yeah, secant squared.
So I'm just going to put in secant squared of 1.
And then it's just tangent.
Okay. And the next one. 4x minus cosecant squared x dx.
Squared dx. So we would get 2x squared plus cotangent.
Good. This is almost like doing proving trig identities. It's starting to look like that. Clearly, you have to know your identities to be able to do these.
Yeah. So 1 minus cosine squared is 1 minus cosine squared. That's sine squared, right? So we can rewrite that. Then we have cosine squared x. We'll have cosine x over sine squared x, which I'm not sure because it's a sine squared on the bottom and it's only a cosine on the top because I know that, so I'm not sure how you would, because cosine over sine is cotangent, isn't it?
Okay. So let's rewrite it. Let's play around with that. So we have cotangent over sine, right?
Yeah.
What's another way to write sine?
Sine could be, I'm trying to figure out what would be helpful in this situation.
Sine is, or 1 over sine is cosecant.
Oh. Then you have cotangent x, cosecant x, which is the derivative of the cosecant.
Negative cosecant.
Well, yeah, negative cosecant.
In other words, if I took the derivative of the cosecant, I would get the negative of this. And notice that it's reversed, which makes it a little harder to recognize. Usually we're looking at the derivative of cosecant as being negative cosecant cotangent. Well, the way I happen to write this, I put the cotangent first and the cosecant second, but you need to be able to spot those. In this part of the chapter, we know that they're going to be relatively easy. In other words, if we know our derivatives of our 6 primary trig functions, we should be able to get all of these by just massaging them like we're doing here. In other words, these don't employ any of the tougher integration techniques. We haven't had to use integration by substitution, integration by parts, any of those things that aren't yet taught to you when you get to chapter 4.1 or 4.2. So we can kind of make the assumption that we'll be able to turn all of these into a simple antiderivative, which is not an assumption you can make for very long. The moment you get harder integration problems, you can never make that assumption. You have to figure out, well, which of the 5 or 6 techniques am I going to employ to do this integration? Whereas we don't have to worry about all that at this level.
So for this one, it's sine x over cosine squared x. And then cosine or sine over cosine is tangent, so we'd have tangent over cosine x. And then we could move the cosine up into secant, so we have tangent secant, and get the answer to the question as secant x, or right?
Yeah.
That's just the reverse of the previous question.
It is, exactly. In fact, if we'd have been really clever, we could almost figured out that it had to be secant. Although, what was the previous? Was it negative or positive? I think the previous was negative, yeah. So it's slightly different. Okay, let's see. We want to find 45. Oh, good. Okay, here let's look at some of these. The graph of the derivative of a function is given. Sketch the graph of 2 functions that have this derivative. There is more than one correct answer. So, what function's derivative is y equals 4?
So wouldn't that just be 4 times any variable, so like 4x plus a constant?
Plus,
you get that?
Right there. In other words, that function, 4x plus c, derivative is the line we're looking at.
So then you would just sketch that function with c being 2 different numbers?
Yeah, exactly. In other words, 4x sketches as a line with a slope of 4, and it could go through that c here, it could go through this c here, basically all of that, and this is what they're talking about when they talk about slope fields. In other words, the antiderivative in 45 is a line with a slope of 4 that goes through an infinite number of y-intercepts. So if you were to plug this in and find the slope field, its slope field would look just like this. Be a bunch of dashes, all with a slope of 4. In other words, in figuring out what these things are up here. These are slope fields, and they're exactly what we're doing in 45 and 46 Okay, so in 46, what is it?
We have the derivative appears to be a line with a slope of 1. So then for equation we would need something that gives us a derivative of f. So then we'd have x squared over 2 plus c.
Exactly. In other words, is all they're really asking us to do here is to define the equation of these graphs and then take the antiderivative of it. In other words, the derivative of this thing that I've circled here would be it would be x, which is this line right here. And of course we can have two different c's, or an infinite number of c's. So the key to each of these problems is let's figure out the equation of what we're looking at here. And then once we figure out the algebraic equation of it, it's real easy to take the antiderivative of it. What's the equation of that line right there, or of that parabola?
So it's a parabola, so it's x squared, and it's been shifted up 2, so that's
it's been shifted up 2. What else has had?
it looks like it's
because y
a little wider
x,
than it should be, like 1.5 times wider.
Well, y equal x squared looks like this.
Yeah.
So
it's been flipped.
It's been flipped mainly.
Yeah.
So as far as I can tell, its derivative, I'm going to start out by sticking a negative sign there. It's negative x squared plus 2. And it's easy enough to tell whether this has a coefficient in front of it or not. The zeros here you can see are at 1.4, which is the square root of 2. So this equation right there fits this curve perfectly. When x is square root of 2, y is 0. So those are my x-intercepts.
So then the equation that the equation that gives us this derivative would then be negative x cubed over 3 plus 2x plus c. And just have two different c's.
Yep.
Now 48 looks to be...
48 looks a little different.
Yeah.
Coming up with the basic equation of 48. Do you know what this looks like? No, the one I'm writing?
No, I'm not sure what 1 over x looks
This is the hyperbolic function. It's definitely one of your 10 basic functions, and it tends to look like this. Okay? Well, this is very similar looking, except it's either the absolute value of that, or more likely it's 1 over x squared, which is a more common function.
1 over x.
My first guess is going to be 1 over x squared, not the absolute value, merely because the absolute value, we're not quite ready for that yet at this point in integration as to how to integrate absolute value functions. So if I'm guessing, I'm going to say 1 over x squared. That point would be on it, 1 comma 1. Also minus 1 comma 1 would be on it. And let's see, when x is 2, we have 1/4. That looks about right. So I'm going to say this is correct. And let's integrate it.
So to integrate 1 over x squared, we'd have, yeah, we write that as x to the negative second, and then we get x to the first over negative, or x to the negative first over negative 1. So
minus 1 over x plus c would be its integral. Now, is it possible that there's a coefficient here, something like a 2? And would that matter? Yeah, it actually would. In other words, if we were really looking at, say, 2 over x squared instead of 1 over x squared, then our antiderivative would be 2 instead of 1. So it is important that we figure out whether that's a 1 or a 2. Well, the best way to figure that out is to try a couple of points. It can't be a 2, because if it was a 2, then the y value would be 2 at that point that I'm pointing at right there. So the fact that 1, 1 is on our graph gives greater credibility to the fact that that curve is y equals 1 over x squared. And the fact that 2, 1/4 is on the graph is even further key. All right. Okay, so we have a differential equation. And they've asked us to find the equation of y. So what's our first step going to be?
Would it be moving the dx to the other side of the equation?
Yeah. And our next step?
Would be to integrate it.
Integrate both sides. And the next
step we would plug in the point, right?
Well, not yet. What's the integral of the left and the right?
We get y equals x squared minus x plus c.
Now we have a point, which you can think of as an initial condition. In other words, this initial condition, all of these curves you see here represent all of the different c's that you can have. A specific c is going to give you a specific point. So to solve for that specific c, plug that point in for x and y, and we'll have what c is.
Then for this, we're plugging in 1, 1.
1 equals 1 minus 1 plus c. C is equal to 1. So the equation they're looking for is that one right there. That is the equation that agrees with that particular slope curve. The next one up is probably x squared minus x plus 2 and plus 3 and so forth and so on.
Yeah.
So that's what slope curves are all about. About 50.
then we would be doing the same process on 50.
Slightly different. They've thrown in a hitch.
Yeah. So, step 1, I would say would be to multiply the 2 through the parentheses and move the dx over. And then take the integrals, so we would get y equals x squared minus 2x plus c. And then we just plug in the 3, 2, which gets us 2 equals 9 minus 6 plus c. So then we get c is equal to -1.
There's the answer.
So that seems pretty...
Yeah, it is. I think you have a pretty good understanding of all of these. Let's look and see what 51 through... Well, slope fields can be a little confusing, but hopefully after the last 4 problems, you got a little bit better idea about them. What they're showing us here is a slope field. The only reason there's a dark line there is because they've expressed an initial condition. In other words, they're saying the slope field we're looking for is this one right here, or this one right here. Well, when you look at slope fields on your calculator, you tend to see them like this. They look more like these lines of dashed, and you can tell that this one here looks like it might be a parabola, right?
Yeah.
You can tell that this one over here looks like it might be a sine wave. This one here looks like it might be some sort of a sinusoidal wave. And this one here looks like it might be the symmetrical of e to the x, or something like that. Okay, so let's go through each one of them here. Let's see what they say. Okay, so 51 really is the same as 49 and 50. They give us a differential equation and they give us an initial condition. It's exactly the same as 49 and 50. It's just the slope fields look a little different, because this is the way it'll look on your calculator if you actually go to do a slope field on your calculator.
So then, for 51, so we would move the dx over first, and then we would integrate it, which gets us y equals, is that 1/4 x squared?
Uh-huh.
Minus x plus c.
Uh-huh.
And then we would plug in the 4, 2 point, which gets us 2 equals 16/4 minus 4 c, which works out to be c equals 2.
So there is the specific slope field, and then let's just take a look. Notice that the curve that we just plotted, y equal x squared over 4 minus x plus 2, is that curve. If we were to finish that off, it would be a parabola that, notice, does not have any x-intercepts, which means it's a quadratic with complex solutions only. Okay. Yeah, I'm not sure what their purpose for showing us the graph is, because we're actually able to do everything analytically here. We didn't need to even look at this graph. Okay, 52.
So 52. 52, again, we'd start off with a dx, and then we'd integrate it, so we get y equals x to the third over 3 minus x plus c. And then we would plug in our point. We get 3 equals negative 1 cubed is negative 1 over 3 plus 1 c. We get 2 and 1/3 is what c is.
And that, I was wrong, that is not a sine function. When I first looked at it, if you look at these things, it looks like it would be kind of a sine function. But the reason I was so clearly wrong is that if it were a sine function, you'd see slope on these hash marks way over here. It wouldn't stop from there to there. So this is more of a cubic function that looks something like this. In other words, that is a typical cubic function, and that fits the pattern of this, and in fact it's going to be the cubic function that goes through that point, comes back, and goes up like that. But there's the precise function. So you can kind of see that just by looking at the slope field, you can't always figure out the function. That's because I misread that. If I had looked at that closely, I would not have said sine. I don't know if I'd have said cubic, but obviously here, what are we going to be looking at here on 53?
Here we do have a sine cosine.
It is going to be the sine function, yeah.
Yeah, sine.
So we've got, after integration, we've got sine x, and 0, 4, 4 equals the sine of 0 plus c. So c equals 4. So we're looking at a sinusoidal function that has been vertically shifted by 4 units. In other words, we're looking at something that looks like this. And that's exactly, if it goes through that point right there, you could see that that's exactly what that will look like. And it goes all the way. It doesn't stop halfway in between like the previous one did.
Yeah.
Okay. And the last one of these. dy equals minus 1 over x squared dx. X has to be greater than 0. What's y equal to?
So y equals That is that. Wait a second. I gotta write this down.
Yeah, if it's
negative
x
x.
to the minus 2.
Yeah, I just had to write it down so I could see it like that.
Well, that's fine.
And then we get plus 1, so then we'd have just x.
x to the
Right.
minus 1,
Yeah, x to the minus 1.
which is equal to 1 over x plus c.
C.
This is the hyperbolic function. And if we look at this set of slope fields here, it's exactly what they're doing, is they're doing this. It's the hyperbolic function. Only they're only showing us one quadrant, but that's okay. And then figuring out what c is, what do we have here?
We have
3 equals 1 plus c. c must be 2. Which means if I was going to graph 1 over x plus 2, well, here's 1 over x. I can eliminate this because they said x has to be greater than 0. So if I vertically shift this by 2, it looks like that. And that's pretty much what that looks like. In other words, if I draw a hyperbolic function through that black point there, it'll come down and it'll have a horizontal asymptote at y equal 2. Okay. Is that it through 54, or did you say higher?
let me go look. I'm not sure. Give me a second.
Okay.
She wanted us to do through to 56.
Okay. Notice that 55 and 56 are exactly the same as 49 and 50 and 51 through 54. The only difference whatsoever is they're not giving us the slope field. Here they gave us a modified slope field. In 51 through 54, they gave us the slope field that you'd get on your calculator. That's what it's going to look like. So in 55 and 56, they want you to use your calculator to generate this slope field, and then using this initial condition, do the exact same thing you did on the previous 6 problems.
Oh, so that's easy.
It's easy as long as you know how to do the slope field on your calculator. What kind of calculator do you have, Chase?
The TI-84, I think, or
Okay.
yeah, one of the Texas Instruments graphing calculators.
Yeah. Unfortunately, I'm not sure I know how to do the slope field on those. You might experiment. If you don't know how to do it, you certainly know how to solve these, right?
Yes.
Okay. Solve them the same way we solved all the others. Here's the way to figure out something on your calculator if you don't know how to do it. Hold on. Let me close out some of these things here.
You figure it out the same way you figure out almost anything you don't know nowadays.
That's exactly right. You go to YouTube. You type slope field on TI-84. It's the Inspire. It's the Inspire CX. Must be one here specifically for the 84. Wow, that's really unusual. There we go, I guess. Huh. Well,
I can.
that's not the one we wanted. We want this one right here.
Let's talk about slope fields. Let's say you
This is actually on the Inspire, not on the 84. You sure you don't have the Inspire CX?
Yeah, I have the TI-84.
Okay, they're significantly different. So let's look at this one. I think this is probably the TI-83 here, but this is what you need to do, is watch a 3 or a 4 minute video and it'll work you right through it.
I'll probably go talk to one of the math teachers at my school and see.
Would actually suggest you do this, because if you can do this, then you can answer any question.
Yeah.
Hold on. Okay, this is the 84. This is a 42-second video. Let's see what it has to say. Looks like he's doing it on both. So it puts in the function, boy, I don't know. Usually it's not this hard to find out how to calculate. Normally speaking, Google is awfully good at taking your instructions and giving you the exact video that you need. This one didn't do it very good. But anyway, that's the way to do it. All right. What else? Anything?
That's it. It looks like.
Yeah, it sounds like you have a pretty good grasp on this material. I expect
This topic.
expect you to do well on that. All right. If you don't have any other questions, let's adjourn, and I'll talk to you next Saturday at 2.
Talk to you next Saturday.
Okay, Chase.
Thank you.
Bye-bye.